We are now on another section of our chapter 7, extended bodies at rest or static equilibrium. If we're gonna go back to our previous lesson, we learned that if we locate a special point in a system or an object, and that special point is called yes, you're right, the center of mass or the center of gravity, and apply a force directly toward or away from that point, the object will not turn or rotate. However, if such force is exerted on a rigid body, multiple forces, the center of mass of the rigid body accelerate translationally or linearly, and the force exerted is independent on the acceleration that causes the object to rotate. We'll also try to use its relevancy to everyday situation, such as how a falling cat able to maneuver landing on its feet even if you drop. I'm not saying you have to, but if the cat drops from its back. So there's a video by Smarter Everyday where they tried to explain that. It's a 6-minute video, so I'm not gonna put that here, but you could go onto his YouTube channel. I also put that link on our physics link, so you just click on that link and search for it. You'll find his video. It's a pretty cool video on how he explains that. It says slow motion flipping cat physics. So look into that. You'll see how relevant our topic is in terms of that particular situation. And also we'll probably wonder why we do have different sizes of tools for tasks that may be different or the same, but it becomes larger. You need a bigger tool for that. Say for example, you just need a small wrench if you're trying to just turn this pipe, but then if you have a bigger one, then you'll need a bigger wrench, obviously. And why do you have to extend this arm here so you can loosen this bolt in here? So those are the things that we're gonna be able to apply. However, this concept that we're going to talk about, which is torque, is everyday. There's physics every day. If you wanna rotate objects, then you will have to apply torque. So you apply torque by opening the doorknob, turning the faucet on, steering the wheel of your car, and this is a whole bunch of physics behind it. So that's about torque. But let's start by looking at this picture here. So we have a top view of a door. You'll see this is the point to which it rotates. We would let's label those. So this is this point to which it turns is called the pivot point, sometimes called the fulcrum or the axis of rotation. So in this case, it is situated at this reference frame, and then forces are applied. So you have force A and force B, which is perpendicular to the length of this system. So this length is called the lever arm or moment arm, which is technically the displacement. That's the perpendicular displacement from the pivot point or from the fulcrum, where the force is acted. So to make an object rotate about an axis, we clearly will have to apply a force. However, it is pretty important that we have to take note of the direction of the force and where it is applied. So if we're gonna look at this, the force is applied going up, therefore the object will rotate counterclockwise. So using physicists' arbitrary coordinates. So moving counterclockwise would be positive, moving clockwise, just to have a little review, moving clockwise would be negative. So that's our arbitrary signs for that. So let's take a look at this. So force A is farther from the axis of rotation, and force B is closer to the force of rotation, to the axis of rotation. So we label them as RB and RA respectively. So if we're gonna look at this, let's say RA is 3 times farther as RB relative to the axis of rotation. So if we're going to look at, again, so if we're going to look at the force being applied, so any force applied will cause acceleration. However, please take note that torque is not force. Okay? Force will make things accelerate. Torque will make things rotate. Okay? Therefore, when it does move translationally and rotate, we call it as angular acceleration. So that's the term we're gonna refer to this. So it is not the same as force. It is another physical quantity that will cause object to rotate. So let's get back to this. So we know that the length, the moment arm, the lever arm, the displacement of RA is, let's say, 3 times that of RB. Therefore, the applied force here would be, given the second law, if we're going to apply the second law, so acceleration is directly proportional to the applied force. And we clearly see that FA is 3 times larger than FB. Therefore, it will have greater rotation, and that is what we refer to now as angular acceleration compared to FB. So if we want both to have the same angular acceleration, what are we going to do with FB? You increase the force by how much? By 3 times. If you want this to accelerate given its displacement is closer to the axis of rotation. So it will require you more force. So let's say, for example, a student is trying to open this door or close this door. It will be what? It will be easier for you to close from here than to close from here. So because of the applied force relative to, because of the torque, technically, because of the torque. So now that we know that angular acceleration is proportional, so angular acceleration, I'm sorry. So the angular acceleration then is now proportional to the product of the force times the lever arm. And this product of force and lever arm is called the torque, which has a symbol tau in Greek alphabet. Thus, we know that acceleration is directly proportional to the torque, which is what? Which is analogous to the second law, which I showed a while ago. Directly proportional to that. But then again, they are not the same. That's pretty important. Okay? So given that, we can now derive a mathematical equation for this new physical quantity called torque. So it is equal to plus or minus the applied force times the radius. And if we look at the object moving, there's going to be an angle to which it will rotate. And also we could plug this concept in terms of angular measurement. So we know, why do we have that? We know that it's the length times the angle, which gives you the radius. That's it. So looking into the angle, that's length over radius. If you want to find the length, that gives you r sine theta. So this is our working equation. And what will be the unit? So what's the unit of force? Newton. What's the unit of length? Base unit in meters. Does this look familiar? Yeah. This is equal to joule, which is the same unit for what? Energy. Same unit for energy, and also for what? For work. But then again, it's not work, it's not force, it's a new physical quantity called torque. So let's take a look at and solve a couple of problems related to this. Okay, so let's take a look at this problem. I need to give a moment. So let's calculate the net torque. So the sum of the torque be in equilibrium equal to 0, or we could write that as net torque. So given that, we have force plus or minus times the radius sine theta, or the length. In that case. So applying the concept of torque, and each force should be oriented so that it's perpendicular to the lever arm, and we call counterclockwise torque to be positive. So due to this 3 torque, this is the only thing that is positive. So this one perpendicular to the lever arm, so that gives us a negative value, and we have a torque that is negative 1.8. So assume that a friction of torque of 0.6 Newton meter opposes the motion. So what are we going to do? So it's opposing motion, therefore we will just do the same process. So plug the same stuff, but we are going to add the friction torque, which is 0.6 Newton meter. So we're going to do that. Then our net force, our actual net force, with this is without friction, this is with friction, becomes negative 1.2 Newton meter. So the friction would be equal to this, which is 1.2 meter. Oh, this is the friction, and then the net would be positive. So it's gonna move clockwise. So this will move clockwise since the friction torque will be opposing the motion moving counterclockwise. So that is gonna be the answer. So let's take a look at another problem here. This is from another textbook that I used to. It's the Giancoli textbook. So it says a level 2, so that means it's a difficult problem. So let's calculate the magnitude and direction of the net torque on this system when it is first released. So we're going to look at the torque. There is a counterclockwise torque due to the force of gravity here, and the clockwise torque due to the force of gravity on the right block. So counterclockwise, clockwise. So So let's call clockwise to be positive, and in this case, so we have sum of, hold on, sorry. So let's look at that. The sum of the torque is equal to 0, so we can call, let's say, clockwise to be positive. And in this case, so we have two masses, so assuming this mass here is the same and the lever arm is massless, that includes the fulcrum, no external forces on the environment, so we have the mass times g times length minus mass times g and the length of 1. So we can simplify this as mg length 2 minus length 1. So that's gonna be our equation for this torque. Okay, just rewrite this here. And we call positive to be clockwise, so we could just write down clockwise here. And that's it.